Okay, so I wanted to do an example of partial fractions decomposition with linear factors of the denominator and with an improper fraction, so you can see how to deal with that. Now, as we mentioned in class, partial fraction decomposition is going to be useful when we're integrating a rational function. What's a rational function? It's a ratio of polynomials. We have a polynomial in the numerator of degree 3 and a polynomial in the denominator of degree 2. This is an improper rational function because the numerator has degree 3, which is bigger than or equal to the degree of the denominator, which is 2. So our first step is going to be to try and do long division to make into a proper fraction. So long division. Okay, so we're going to divide the denominator into the numerator using long division. This is just like long division of numbers way back in elementary school, except for, of course, numbers have zeros in the appropriate places when there's no non-zero term, and we usually just leave out the zero terms in the polynomial. But in long division, you want to add those in. So you've got x cubed. So since there's an x cubed term, there should be an x squared and an x term as well. So I'm going to add those in. And of course, we also have a constant term. Now, in the denominator, all the terms are present, so we don't have to add any zero terms. So what is the idea here? I'm going to take the leading term in the denominator and decide what I need to multiply that by to equal the leading term of the numerator. And of course, it's going to be a constant times some power of x, or a constant, and it's because it's an improper fraction. And in this case, it's going to be just x, right? If I multiply x squared by x, I get x cubed. So now I'm going to multiply that x all the way through, and I get x cubed minus x squared minus 6x. And then I subtract that off from my original thing. I subtract the whole thing off, so x cubed minus x cubed, 0. 0 x squared minus x squared is going to be plus x squared. 0x minus 6x is going to be plus 6x. Bring down that negative 1. Now I added the 0x squared and the 0x. That allows me to combine like terms. That's what allows me to simplify this when I do the subtraction. Okay, again, my remainder has degree 2. The original divisor has degree 2. So it's still improper. We need to take it one more step. I want it to have a smaller degree remainder. And what do I multiply by x squared to get x squared? That's just 1. And I get x squared minus x minus 6. And I'm going to subtract that off. And when I take x squared minus x squared, that's 0. That's why I chose 1, right? 6x minus x is 7x. Minus 1 minus 6x minus x is 7x. Minus 1 minus, that's minus 1 plus 6 is going to be plus 5, right? Now my remainder has a smaller degree, so I can write that as a fractional remainder. 7x plus 5 over x squared minus x minus 6. Okay, so let's go back to this original fraction. So what we just did is said that original integral is now equal to x plus 1 plus 7x plus 5 over x squared minus x minus 6 dx. Okay, so let's just analyze this. We know what the integral of x is, right? That's just x squared over 2. We know what the integral of 1 is. That's just x, because x is the variable of integration. So now we need to focus on what the integral of that fraction is. And that's where partial fraction decomposition is going to come into play. So let's get this part out of the way. Move that way down below. Way down below here. Come on, go down, go down, go down, go down, go down, go down. Okay, and now let's come back up here. Okay, so I want to decompose this proper fraction, so partial fractions now. I want to decompose, let's move this down lower so I'll have time to move above it. That partial fraction into, more simple fractions. So I'm going to write 7x over x squared minus x minus 6. First step is to factor the denominator completely. And that denominator, you may notice, factors into x plus 2, x minus 3, right? I chose it so it would factor easily. Of course, it's a quadratic, so you can always use the quadratic formula to factor it or to determine if it factors. So our goal here is to say, well, this is going to be written as a sum of two simpler proper fractions. Something over x plus 2 plus something over x minus 3. And if these are proper, that something can be only some sort of constant, right? We'll call it a and b. So if it's a proper fraction, that's going to be a constant. Okay, so as long as you factor into linears, only linears, then you're going to have those constants as proper fractions. And the goal is to figure out what a and b are, so when I add these two fractions, I get 7x plus 5. Well, I'm going to add these. Of course, you add fractions by finding a common denominator, and the common denominator is the product. Just a minute, that should be a minus. Okay, x plus 2, x minus 3. And how do I find that common denominator? Well, I multiply numerator and denominator of the first one by x minus 3, so I get a times x minus 3. And I multiply the numerator and denominator of the second term by x plus 2, so I get b times x plus 2. So again, we want to solve for a and b so that 7x plus 5 is equal to a times x minus 3 plus b times x plus 2 for every possible x. For every possible x. And we use the fact that it's true for every possible x to solve for x. So since these are linear factors, we can actually, the easiest way to do this is to choose the right values of x to plug into this, expression to solve for a and b. Okay, so notice that if I try x equals, no, I don't want to do that. If I try x equals 3, well, on this side here, I get 3 times 7, 21, plus 5, which is 26. And over here, well, if I plug in 3, this thing just goes to 0, right? And so I'm left with b times 3 plus 2, that's going to be 5b. So b has got to equal 26 over 5. Okay, and now if I try x equals negative 2, well, again, negative 2 times 7 is negative 14, plus 5 is negative 9. And if I plug negative 2 in for x in that first term, I'm going to get negative 2 minus 3, that's negative 5a. And the next term zeroes out. That's why I chose negative 2, so a is equal to 9/5. So in other words, what do we have here? We have that 7x plus 5 over x squared minus x minus 6 is equal to a times 1 over x plus 2. So a is what? 9/5 times 1 over x plus 2 plus b was 26/5 plus b 26/5 times 1 over x minus 3. Okay, so let's go back to our original integral. What does that help us? Well, this can now be written as the integral of x plus 1 plus 9/5 times 1 over x plus 2 plus 26/5 times 1 over x minus 3 dx. And this I basically know how to integral. Great. Now in the last two terms here, in this term and this term, you might try u substitution. Like you could try u equal x plus 2, but then du is just dx. I'll let you, if you're having trouble following it, just go ahead and try that yourself. And in this term, you could try u equal x minus 3, and du then would just be dx. Go do that on your own and convince yourself that you're getting what I say you're getting when you integrate. So I integrate x, I get x squared over 2. Since those are just sums and differences, I can just integrate them separately. I integrate 1, I just get x. I integrate 9/5 times something, I get 9/5 times the integral of that something. And it's going to be 1 over u integral, right? So that's ln u being x plus 2. And 26/5 times something, integrate that. That's 26/5 times the integral, which is ln x minus 3 plus c. And there we have it. All done. All done.